In this session, we're going to solve equations with radical expressions. Our first example, solve the square root of x minus 4 plus 4 is equal to 7. First pitfall I want to alert you to. Folks disrespect the radical. They see the negative 4 under the radical and the plus 4 outside of the radical, and they somehow think that they can combine those two. But that's not the case, so don't do that. What I'd rather do is isolate the square root. And I'm going to do so by subtracting 4 from both sides to give me the square root of x minus 4 is equal to 3. Now, solving equations of this type is all about undoing what's been done to the variable. Right now, it's inside of a square root. And so what I'd like to do is square both sides. On the left-hand side, that'll give me the radicand, x minus 4, and on the right-hand side, that'll give me 9. And then finally, adding 4 to both sides will give me that x is equal to 13. When we square both sides of an equation, we have to beware what's called extraneous roots. These are solutions that you get by solving something that don't actually turn out to solve the equation. So it is a good idea when solving equations with square roots or equations that you have squared to check our solution, and that's going to be done by substituting the value 13 wherever we see x in the original equation. And so I'm going to check to see if the square root of 13 minus 4 plus 4 does indeed equal 7. And working through our steps indicates that we do end up with 7 on the left-hand side, 7 on the right-hand side. And since 7 equals 7, we can say with confidence that x equals 13 is the solution. Next, we're going to solve the square root of m squared minus 11 plus 5 is equal to m plus 4. As before, what I want to do is isolate the square root. And in this case, what that means is that I'm going to subtract 5 from both sides of the equation, keeping like terms with like terms, And I have this square root of m squared minus 11 is equal to m minus 1. As before, I'm going to square both sides of the equation, noting that on the right-hand side, what we're squaring, m minus 1, is a binomial. For this, we need to remember what happens when we square a binomial, and we need to remember our f word. We need a FOIL. On the left-hand side, we have m squared minus 11. On the right-hand side, after we square that binomial, or maybe we remember the pattern for a perfect square trinomial, this is going to end up being m squared minus 2m plus 1. And oh, lucky us, when we subtract m squared from both sides, they end up dropping out and completely. And we have negative 11 is equal to negative 2m plus 1. Now I'll subtract 1 from both sides to get negative 12 is equal to negative 2m, and divide both sides by negative 2 to end up with m is equal to 6. I encourage you to check your solution, or our solution, in the original equation by, as we did before, substituting 6 in place of m everywhere it appears, and making sure that you actually get a true statement where the left-hand side does equal the right-hand side. I am going to move on to the next example, which is solve the square root of n plus 4 plus the square root of n minus 1 is equal to 5. It's tempting to square both sides right now. If we did, though, we would be squaring a binomial on the left-hand side. I don't want to do that. The reason I don't want to do that is because I would end up with the first radical squared, but then plus 2 times the first radical times the second radical plus the second radical squared, right? In keeping with the pattern for squaring a binomial. I don't think we've done ourselves any favors by having 2 times the square root times the square root. So that's not what we're going to do. What we are going to do is start to sound like a broken record. We're going to isolate a radical before we square both sides. I'm going to do so by subtracting the square root of n minus 1 from both sides. Now, I don't have like terms, so it's not going to be pretty or nice, but it won't be as bad as what we just saw. And here we have the square root of n plus 4 is equal to 5 minus the square root of n minus 1. Now I'm comfortable squaring both sides. We're still going to have that squaring of a binomial on the right-hand side because we have the binomial 5 minus the square root of n minus 1. On the left-hand side, squaring this radical gives us n plus 4, right, the radicand. On the right-hand side, though, let's remind ourselves of the pattern. And what we're going to end up with is the first term squared minus 2 times the first term times the second term plus the second term squared. This is going to simplify and become n plus 4 is equal to, and on the right-hand side, 25 minus 10 times the square root of n minus 1 plus the square of the square root, so it just pops out the radicand n minus 1. Now we're going to subtract n from both sides, and 25 minus 1 on the right-hand side adds up to 24, so I'll end up subtracting 24 from both sides as well, because what I want to do is, as before, isolate, in this case, just the radical term. So on the left-hand side, we have negative 20, and on the right-hand side, we have negative 10 times the square root of n minus 1. This seems like it's set up pretty well for us to divide both sides by negative 10 and completely isolate the radical. I'm going to make a couple of notes about this in a few minutes. But for now, we're going to say on the left-hand side, negative 20 divided by negative 10 is going to give us 2. And on the right-hand side, we have the square root of n minus 1. If you think we're going to square both sides again, you're right. And so we have 4 is equal to n minus 1. And then finally, we're going to end up with n is equal to 5, which we should check. And we would check it by substituting 5 in place of n in the original equation. We've squared this thing twice. The odds of this not actually being a solution are actually pretty good. But you'll find that it works in this case and we're good to go. A couple of things I want to point out. In this case, in that step where we subtracted n from both sides, we ended up with no more variable. It is perfectly conceivable, though, that we would have ended up with a binomial on the left-hand side for which we would have to remember the F word and FOIL, right? So that is a possibility that could come up. Beware of that, number one. Number two, when we divided both sides by negative 10, we ended up getting rid of the coefficient that was attached to the square root. Had that not happened, for instance, let's scroll down. Suppose we had had, I don't know, something like negative 20 is equal to like negative 7 times the square root of n minus 1. I would not want to divide both sides by negative 7 because then I'd have a fraction on the left-hand side, and that's not sweetening the deal for me. In this case, squaring both sides would mean that on the right-hand side, I'm going to square the 7 and then square the square root of n minus 1. So I'd have 49 times the quantity of n minus 1. On the left-hand side, I would have 4, we would just keep going. Since that's not what we're looking at, we don't have to, take that to completion. But I just wanted you to be aware that sometimes you're going to have to FOIL even after you've isolated a radical. And that if you have a coefficient in front of the radical you can't easily divide out, then we need to remember our properties of exponents. Let's get rid of that. And our solution is n equals 5. Next, we're going to solve 3x plus 1, the quantity to the 1/3 power, plus 2 is equal to 0. Not fair. This is about radicals. Yeah, that 1/3 power represents the cube root of 3x plus 1. So it's a radical, which I want to isolate. So I'm going to subtract 2 from both sides, leaving me with, if you like, the cube root of 3x plus 1 is equal to negative 2. We didn't have to take this into the cube root world. If we hadn't, we would have the same thing, essentially. 3x plus 1 to the 1/3 power is equal to negative 2, right? We would have isolated the term that had the fractional exponent. Where we see the one with the cube root, it should make sense that we're going to cube both sides, in keeping with what we've been doing, which is undoing what's been done to the variable. And we will end up with 3x plus 1, because cubing a cube root eliminates the radical. And on the right-hand side, negative 2 cubed, it's going to be negative 8. Let's just go ahead and finish this off. So we have that 3x is equal to negative 9, and x equals negative 3. As a matter of good form, we should check our answer just because we've solved an equation, but we aren't going to run the risk of an extraneous solution with cubing. That only happens with even indices, mostly because squaring washes away negatives and squirrely things can happen. Now this other one that we had, where we wrote it down as 3x plus 1 to the 1/3 power equals negative 2, we could think of it as, I want the exponent, which is now 1/3, to be a 1. How do I make a 1/3 become a 1? The answer is I would multiply the exponent by 3. In other words, I would still be cubing both sides. I just wanted you to see how we might handle it if we had a rational exponent indicating a radical. Last, I have an example I'd like for you to work. It's the square root of 4x plus 1 minus the square root of 2x plus 1 is equal to 2. You'll find this is similar to an example you saw a couple of examples ago, but I'd like for you to pause the video and work this out on your own. So the first thing I'm going to do is isolate the first square root and then end up with the square root of 4x plus 1 is equal to 2 plus the square root of 2x plus 1. And then we're going to square both sides, popping out the radicand, 4x plus 1 on the left-hand side, and taking care to square the binomial, applying that pattern. On the right-hand side, we have 4 plus 4 times the square root of 2x plus 1 plus 2x plus 1. Now I'm going to, again, isolate the radical term by subtracting the 4, the 2x, and the 1 from both sides. That leaves me with 2x minus 4 is equal to 4 times the square root of 2x plus 1. At this point, I'd like to divide. I'd like to divide by 4. I'd like to avoid a fraction. I have to take my pick. What I'm actually going to end up doing is I'm going to divide all of the terms on both sides by 2. Because all the coefficients are even, that's the best I'm going to do without introducing a fraction. When I do that, I have x minus 2 equals 2 times the square root of 2x plus 1. Now that I have the radical term isolated and I've cut all the coefficients down to size, I'm going to square both sides. And on the left-hand side, that means I'm going to FOIL. We have x squared minus 4x plus 4. And on the right-hand side, we're going to apply our properties of exponents and end up with 4 times the radicand, 2x plus 1. Now I'm going to distribute and get everything on the same side of this quadratic equation. When I do that, I end up with x squared minus 12x is equal to 0. Finally, I'm going to solve this by factoring out the x. We have x times x minus 12 is equal to 0, which gives me that x is equal to 0, or x is equal to 12. Again, we have squared this equation twice, so I want to check our solutions, which I'm going to do by substituting each value into the original equation in turn. For x equals 0, we end up with the square root of 1 minus the square root of 1, which certainly does not equal 2. X equals 0 is not a solution. For x equals 12, we have the square root of 49 minus the square root of 25. Does that equal 2? If it didn't, we'd say no solution. But since 7 minus 5 does indeed equal 2, we have that true statement that we're after, and so x equals 12.